90 bits of security, and it'd be about the same as RSA 1024, except about half the size. To verify, it's pretty easy. We compute two values, U1 and U2. U1 is just E over S, so E is the hash of the message over the S parameter they gave you. U2 is R over S, and R and S are what the signature actually is. And then from that, we do a two-point multiplications, an addition, and we do a comparison. I work at the math on the slide, but I'm not going to read it out here because we want to save some time. But if you guys want to check it out later, it's there. It's also in my libtomcrypt libraries. That's another good, if you like C source code over English. So if the values compare, your signature is valid. If not, then all bets are off. There's three standard bodies that discuss ECC crypto. NIST kind of just packages up things they find. So they specify 5 prime field, 5 binary field curves. Don't really worry what that means. It's just two different ways of doing, it's two different representations for the math, sort of. The Suite B stuff, if you ever heard of the NSA Suite B ECC crypto, that's the prime field curves from NIST. The prime fields are nice in software, which is why a lot of people like me, for example, dig them. You're using things that the processors will have, so an integer multiplier, an integer addition, so on and so forth. The binary fields are better for hardware because you're going to be doing weird things like binary field multiplication, which is not something the average CPU has, so it's pretty slow. It can be done, like OpenSSL, for example, was one of the first public libraries that had ECC in it, and they did binary field curves first. It can be done fast. It can be done faster in RSA, which is nice, but I like prime field better. NIST doesn't standardize much on Diffie-Hellman and DSA. They pretty much just refer to ANSI and say, whatever ANSI's doing this week, it's good for us too. And then ANSI went out and they wrote 2 specs. X962, which is Diffie-Hellman and key storage, and X963, which is ECDSA. The key storage in X962, so if you see the comment there, it's utter crap. They have a way of representing their keys that's not uniquely decodable. So I can hand you a blob and you won't know what curve it belongs to or any of the like sizing parameters or anything like that. So it's just 2 numbers concatenated together with anything else. Whereas X963, you send that 1, which is a standard way of encoding data so that's uniquely decodable. I can hand you anything in ASN1, you can figure out what it is. The ANSI specs aren't free. I managed just to get myself a draft copy off some weird Chinese website or something. The way it should be, right? Why would I pay them? And very few applications actually comply with X962. At the time when I was reading up on it, it was a draft. So obviously, any company that was really working on it would be still, in development. Obviously, it wouldn't be public at that point. And in particular, my approach for things like key storage, I just use ASN1. And if my users really want to be X962 compliant or whatever, they can sort it out on their own. They're not paying me, so what do I care? The IEEE standard P1363, again, isn't free. It's really redundant because you have ANSI and IEEE kind of dueling banjos with elliptic curve. And IEEE is more restrictive, and if you're not a big organization, it's more expensive to deal with. And generally, for people like me, I learned how to do ECC just from random papers on the web, books, stuff like that. And the standard body wasn't useful for me at all. So, just ignore them. The NIST curves, the prime field ones, go 192 bits through 521 bits to deal with the key sizes that AES supports, so 128 through 256, and the SHA sizes. They use I don't know how to read this comment here. They use a style for their modulus, which is known as diminished radix. Basically, they're trying to make the math a little faster. Nothing really in particular there. All the curves have prime orders, which is useful. So for those who know how to implement Diffie-Hellman, for example, your subgroups have to be prime order for security reasons and all that. And in this case, the NIST standard or NIST curves do that as well. So the NIST curves all have prime orders, so you don't have to worry about that. And at the bottom, there's an example. That's P192. So that's the parameters, the prime, the order of the curve, and the base point, whatever. I'm, again, not going to read that aloud. So let's move into patterns. Everyone loves patterns. And my talk. There we go. So Toorcon is kind of the patent whore of ECC. And they're the people I love to pick on because they don't know what they're talking about, but they love to talk about it. So they have a series of patents that cover everything from how to to what to implement, when to implement it, and all that stuff. And they're not very original, but it's because they're a small-minded group and everything. So I listed off a couple of their patents that I found were totally funny. The first being a crypto ALU. So this is basically your standard issue ALU, execution ports, register file, sequencer, all that jazz. And apparently, because you do a polynomial multiplication in it, it's now something you can patent. And then they have a couple others like that, and then multiplication patent and all that. Long story short, you're doing Suite B style ECC. So this is prime field curves. You're more or less safe. So I already picked on the ALU. So the classes of their patents, if you ever want to get into implementing this stuff, follows along the lines of power-sensitive work, hardware designs, signature and encryption, and the actual math that goes into implementing this. The power-sensitive side is things like differential power analysis and static power analysis, so DPA, SPA, resistance. For side channel attacks where you'll have a device that leaks a certain amount of information through the current it draws or the heat it generates. They're easy to avoid because they're very specific designs. They're good to know about, though, because they give you tips on how to implement it yourself. Their hardware patents cover things like their ALUs and their multipliers, but the designs themselves are pretty much, textbook at this point, so the validity of their patents is kind of in question. They have an algorithm called MQV. It's the initials of the authors of the algorithm, I believe. And it's an authenticated encryption algorithm. Basically, it does signatures and encryption all in one step. It's not part of the ANSI standards. So if you have to do signature encryption, just use Diffie-Hellman and DSA. It is part of Suite B, though. So that's kind of a hazard. If you want to actually be compliant with the NSA Suite B protocol, you'll have to actually have an MQV license if you don't fall under the NSA umbrella for that. The math stuff, mostly it touches on the binary curves, which is another reason why I avoid them. They have various representations that I won't go into, but that's where their patents fall. If you avoid binary fields, you're all set. And of course, if you're paranoid, you can do things like I did. Become a public domain hippie. I give everything out for free, and like hell, they're going to sue me. And they haven't yet, and I've been doing this for 5 years, so I guess it does work. And the other way is just to avoid the specific algorithms they have patents on. You can do that and still be compliant with the NIST and the ANSI. So if you have to market crypto out there, you can still do it safely. On the copyright front, Toorcon does have their standard issue ECC library, but you don't have to use it, and in fact, you should use mine. But now there's two. So there's libtomcrypt that supports DSA and Diffie-Hellman. Yeah, I won't read that part, but you can see it. But I have the essentially Suite B minus MQV. So the code is well documented. It's pretty fast too, as we'll see shortly. It's free for all purposes. It's worth looking at. Even if you just want to learn about the math, it's a good resource, I think. Of course, I wrote it, but if you don't want to take my word for it, there's other crypto libraries out there, like Crypto++ by WeDie, and he implements the binary field side of things, and I think he does touch on Prime, but I don't know off the top of my head. The collection of source code in Crypto++ is copyrighted as a whole, but the individual components are free to use for any purposes whatsoever. They're kind of public domain that way. So if you rip code out of Crypto++, you're pretty much safe. But he doesn't really go after people to use it anyways. He wants people to use it, which is nice. And it also delivers a mighty blow of justice to the commercial world. And if you really want to get onto the devious side, you can find copies of BSafe. They started getting into ECC and what have not, and pick on them a bit. Or if you want to get historical, you can look for RSA ref and just laugh at that code because it's pretty horrible. They wrote it. Back up a bit. RSA ref, it was RSA's way of saying RSA is really, my talk here where I'm talking about ECC is what RSA did in the 90s to say RSA is really easy, except their source code looked like it was written by the average 12-year-old. So it was slow and horrible, and things like OpenSSL were way faster even back then. So them being the leaders of RSA was kind of awkward for that. So let's get into some math before we wrap up this talk. There's still like 10 slides up, whatever. So we want to point multiply. We want to do efficient point multiplication because point multiplication is what we base our signatures and encryption off of. And we want to do it efficiently and fast, obviously, so we can use less power and get things done quicker. To do this, it usually involves the first thing you want to do is make your point addition and your point doubling fast. So what we're going to do here is you're going to use different algorithms for that. So the standard textbook way, what you would do using only high school algebra is what's known as affine mathematics, where you'd find the slope of the line or the slope of the tangent, plug that into an equation, figures out for the x-coordinate. Unfortunately, while this is accurate, very compact code, it's slow because you have what's known as an inversion. An inversion is simply a mathematical way of saying you're going to 1 over x. So usually in finite fields, you don't have a division algorithm. You find the inverse and multiply out. Inversion is very, very slow. On most platforms, you can multiply an equal sized number about 20, anywhere basically from 8 to 20 times faster than finding the inverse. So we want to in this operation. So a basic point add is 1 square, so the s there is a square, m is multiply, and I is inverse. Point addition is only one of each. So you think there's only 3 operations, that must be fast. No. Point doubling is basically the same thing. There's 2 squares, a multiply, and inverse. If we based ECC today off using affine systems, you might as well use RSA, because it'll be faster, even for numbers that are 8 times smaller. Inverse is just that bad. So what we're going to do instead is use what's known as projective coordinates. And without getting super hot on the math, basically you're projecting it onto 3 space, and we're going to do point addition and point doubling with more basic squaring and multiplication steps, but no inversions. And in this case, point addition is 8 multiplications and 3 squarings, no inversion, and point doubling is 4 multiplications and 4 squarings. It may seem like more work, but it isn't. So the basic multiplication is the same way you do RSA or Diffie-Hellman. So you'd have a simple multiply and square algorithm. You'd be inserting 1 bit at a time of the exponent into the final result. It's very simple. It's complexity efficient. So if you have very little space to code things in, it's what you want to do. But it's so very, very slow. Bad. So the next step up is to do what's known as a sliding window. And again, this is an algorithm you do with RSA. And essentially what we're doing here is we're going to be doing the same amount of doubles, but we're going to group up additions into one step by looking through a table. So instead of adding, depending on whether 1 bit is set, we'll add a different value based on, say, 4 bits of the multiplicand. It's slightly more complex, but it's a lot faster. And if you have the RAM to fit it, it's good. So can we do better than simple sliding windows? And it turns out the answer is yes. And I do have graphs to prove it. Yes. These are other point multiplication algorithms, but since we're running out of time, I'll skip over them. So basic fixed point, I'll try to go quickly through this, is say you want to multiply that 16-digit number that probably no one past the 3rd row can read. You want to multiply that by your basic G point. So I broke it up into 4 groups of 4 bits, because what I'm going to be using here is known as a 4-bit window for the fixed point multiplication. So what we do is we pre-compute a table where we fill in the 4 bits, if you can see it. So there's a whole bunch of zeros, then an X, and then a whole bunch of zeros, and another X, and what have not. We have basically 4 digits with the lower bit set. We step through all 16 possible values of those 4 bits, pre-compute the value. Since the base point there is your public key or the NIST point, we already know what G is. And then we can put that aside. So we can pre-compute that anytime, store it aside, use it for later. Now to do the actual point multiplication, again, using the value at the top there, what we do is we look at the 4 groups of 4 bits, and we take the top bit, the most significant bit of each one. And in this case, it's going to turn into be the bold underline number in the bottom row here, if you can see it. So in this case, 100, or yeah, 1 3 zeros. We take that value, the 4 bits there, plug it into our table, and store that as our initial result. So now we have a starting point to do the rest of the point multiplication from. The next step, we double that. So now we look up and store, and then double it. And then the next step is we look at the most significant